Welcome to the video series of System Programming and Compiler Construction. We have already completed two videos on the fifth module, that is Compilers and Analysis phase. In the previous module, I completed the analysis phase, which constituted of four steps, that is lexical analysis, syntax analysis, semantic analysis, and intermediate code generation. Just to revise, the lexical analysis is considered to be the first step under phases of compiler, or we can also say it is the first phase under phases of compiler. Target code generation is the last step under the phases of compiler. Lexical analysis is responsible for generating stream of tokens, which is submitted as an input to syntax analysis. Syntax analysis is responsible for generating parse tree. Semantic analyzer is responsible for generating semantically verified parse tree. Intermediate code generation is responsible for generating intermediate code. Till this much we have already completed in our previous videos. In this video, we will understand how a code is optimized, why code optimization is required, and how to convert an optimized code into target code. As mentioned on the slide, analysis phase is known as the front end of the compiler and it is machine independent, whereas synthesis phase is the back end of the compiler and it is machine dependent. Let us see what is code optimization. As I said, code optimization is the first step under synthesis phase, or it is the fifth phase of the compiler, and we have already seen it is machine independent. Code optimization basically tries to improve the intermediate code so that the better target code will be generated. Why we need the target code should be better? Because the target code is dependent on the underlying machine. The target code has to make sure that it uses minimum possible resources. What kind of resources I'm talking about? The target code should make sure that it uses minimum registers, because these registers are obviously involved in some or the other task. So the resources that is used by the target code should be minimum. And for doing that, this step of code optimization is very important. Thus, optimization involves removing of unnecessary lines of instruction and rearranging the statements in such a way which will speed up the execution of program and it will not waste any resources. How the intermediate code is converted into optimized code, or how do we generate an optimized code from the previously created intermediate code? Please pay attention. The first instruction, that is the first 3AC instruction, is T1 is equal to int to float 60. This can be converted into 60.0. Thus, the instruction can be rewritten as T1 is equal to 60.0. Now, this value 60.0 can be directly substituted at this point. Hence, my next instruction will be T2 is equal to ID3 into 60, T2 is equal to ID3 into 60.0. If you observe, this T1 variable is no longer used. Hence, the second equation will be replaced by T1 because T1 is no longer being used for assigning the value of 60.0. Hence, we are not going to create a new variable T2. Instead, the previously created variable T1 is used and the first instruction is created. Next, the instruction will be, now because my destination of ID3 into 60 is T1, my third instruction will change. It will be written as T3 is equal to ID2 plus T1. If you observe the fourth equation, it is just an assignment operator. Thus, by combining the third and fourth operation, I can get my new instruction as ID1 is equal to ID2 plus T1. Hence, my optimized code will be T1 is equal to ID3 into 60 and ID1 is equal to ID2 plus T1. If you observe, in intermediate code, we had 4 instructions to be executed and 3 different variables which are used. Thus, the number of registers used will be more if I use the same 3AC to convert to target code. But if you observe the optimized code, the number of instructions are reduced. Also, the number of variables which are used are also reduced, thus saving the resources. The optimized code is then sent as an input to target code generation. The target code generation is responsible for creating assembly code. Let us see how does it do. The target code generator takes as an input the optimized code of the source program and it maps it into the target language. The objective of this phase is to allocate storage and generate relocatable machine code. It also allocates memory locations for variable. What do you mean by memory locations? Ideally, whenever an assembly language program is written, the variables cannot be used directly. Instead, the values of the variables needs to be stored in some registers. That is nothing but allocating memory locations for variable. The instructions in the intermediate code are converted into machine instruction. A crucial aspect of code generation is the judicious or careful assignment of registers to hold variables. Let us see how target code is generated. So this was my optimized code and this is my equivalent target code. Let us understand. The first instruction over here is ID3 into 60.0. As I said, you cannot multiply the value of a variable in assembly code. Hence, the value of variable ID3 has to be first loaded into some register. And that is done using the first instruction, that is LDF. Now, why F is written? F means the floating point numbers. So, because we are loading the floating point value, we write F at the end. Thus, LDF stands for loading the content of ID3 into register 2. Then we can multiply. So what are we multiplying? Contents of R2 with 60. Now why hash is written? Because the system should consider it as a constant. So again, F is written because I am multiplying a floating point number. So multiply the contents of R2 with 60 and the result will be saved in R2. The next instruction is what? ID2 plus T1. Again, ID2 is a variable. Hence, we will first load the value of variable ID2 into register R1. Then we need to add R1 and T1. So, what you're doing is, it is addition R1 comma R1 into R2. This means R1 and R2 will be added and the result will be stayed in R1. Lastly, the code is responsible for, the target code will be responsible for storing the register R1 value into ID1, because whenever we are printing our final value, we always print the value which is there in the variable. Hence, the register, whatever value is there in the register, has to be stored back into the destination variable, which is ID1. This is how optimized code is converted into target code. So these are some questions which I have gathered from various university papers. I've gathered from Mumbai University paper. If you observe, the question says, explain the phases of compiler, discuss the action taken in various phases to compile the statement. In other words, you will have to first explain all the phases of compiler starting from lexical analysis till target code generation, and parallelly you should be explaining what will be the output for this instruction after every phase is completed. So I will be solving this now and the remaining two will be shared with you all once you comment down for solution. Let us see the solution. This is the equation that we need to solve for phases of compiler. The 6 phases of compiler are lexical analysis, syntax analysis, semantic analysis, intermediate code generation, code optimization, and here I will be doing the target code generation. Lexical analysis is responsible for identifying lexemes and converting each lexeme to its token. So the lexemes identified in this case are A equal to B star C plus and 10. Since A is an identifier, it will be given a token with name and its value. Equal to, being an operator, does not have any value. B again an identifier, B again an identifier will have name and value. Star, an operator, will not have any value. C, an identifier, will have value and name, plus an operator, no value. 10, a literal, will be written in the angular bracket. Then we go to syntax analysis. Syntax analysis is responsible for creating a syntax tree based on how the expression will be evaluated. So B into C will be evaluated first. Hence we create a tree for B into C operation. So B becomes my child, C becomes my child, and star will be the root of the tree which is created. Then 10 will be added to the answer of B into C. 10 being on the right hand side of the equation on my tree, it will also hold the position that is on right hand side. So I have a plus sign and then it is connected to the children. The entire solution is saved in a variable A. So the tree finally will be of this type. Next is semantic analysis. Semantic analysis is responsible for generating semantically verified parse tree. In the question it was mentioned A, B, C are of real type. Hence, we need to convert 10 to real type. So entire tree will remain as it is except for 10 will be converted to real. So this is plus. Then I have star. Then here I will include int 2 real and then I will have 10 and then remaining part of the tree B into C will be written as it is. So this is how a semantically verified tree is created. Now what we do is we start creating intermediate code. So intermediate code, what you have to do is you will have to convert int to real first, because when I travel my tree and I observe that the last node is int to real, so the intermediate code will be t1 is equal to int to real and in bracket I will write 10. Then the next operation will be t2 is equal to b into c. If you remember, 3AC makes sure that there is only at most one operator on the right hand side, and on every operation a new variable is created. Then I will say T3 is equal to give me a minute. Okay, so it is T3 is equal to, this is B into C, I forgot, and T3 is equal to T2 plus T1. T3 is equal to T2 plus T1, and then this result is saved in A, so A is equal to T3. Now we need to convert it to optimized code. So what we do is we first write T1 is equal to 10.0. Okay, then T2 is equal to B into C. Now it is T3. Okay, but here instead of T1 I will write T2 into 10.0. Okay, I'll write T2 into 10.0. Now T1 is no longer existing. What I do is I change this particular T2. I'll change this T2 to T1. I'll change this to T1 because this is no longer existing. And I will again change this T2 to T1. This T2 will be replaced by T1 and this will be now becoming T2. So it is T1 is equal to B into C and T2 is equal to T1. And the last is what? A is equal to T2. A is equal to T2. So if I want to write my final optimized code, then I'll write it with another pen so that it becomes clear. So my final optimized code will be T1 is equal to B into C, and these two equations will be combined to write A is equal to T1 plus 10. Okay, there's lack of space is there. I'll rewrite it once again. And it was T1 plus 10. My bad. I'm sorry. This was T1 plus 10. And I'll rewrite the equation. So I'm sorry, but because of lack of space, I was not able to write. So T1 is equal to B into C and A is equal to T1 plus 10.0. So the code which is written in red is my final optimized code. Next, we will need to write the target code. So for writing the target code, I'll write it here. So my target code will be now how do I write my target code? First, I will have to load the registers with value of B and C because B and C being my variable, I will have to first load the value of these variable into register. So I have loaded it. Now I will perform the first operation, that is to multiply. So I will write multiply R1 into R2. Then what I will do is then this so I have written the target code for T1 is equal to B into C. Now what I do is I will write add R1 because my result is in R1 comma I'm sorry it is R1 comma hash 10.0, and lastly it will be storing this result in a stf a comma R1. So this is how we generate our target code. Okay, so I'll try to put the screen together. So if you observe, the entire solution is on the screen: lexical analysis, syntax analysis, semantic analysis, intermediate code, and target code. Sorry, code optimization and then the target code.